So in our last video, we discussed a number of applications of algebraic eigenproblems, and in this video, we're going to start looking at how we actually get these eigenvalues and eigenvectors. So remember the geometric interpretation. We have a matrix A, it's n by n, and we're looking for the vectors, the special vectors u, that A transforms into itself. So multiplying A times the vector returns the same vector back, but it's just been scaled by a factor lambda. Lambdas are the eigenvalues, the u's are the eigenvectors. So just to emphasize how special these eigenvalues and eigenvectors are, for a given A matrix, any arbitrary value of lambda is going to give only the trivial solution. The only solution for u that will satisfy this eigenrelationship, the system of linear algebraic equations in this form, will be 0, except for the n, capital N, the same number as the size of A, vectors that only get stretched by the matrix A. And that's what we're looking for. So those give rise to the eigenvalues and eigenvectors. Sometimes they're called the characteristic values. Characteristic vectors, eigen comes from the German. So we don't want the trivial solution. We do not want the solution where u is equal to 0. So we're looking for the lambdas that give us non-trivial, non-zero u's. Again, graphically, you can think of this as taking the original vector, u, and simply stretching it by a stretch factor, lambda. And we'll use that geometric interpretation over and over again to better understand what we're doing. Okay, so how do we actually solve it? Well, we have AU is equal to lambda u. I want to make the right-hand side the same size and shape as the left-hand side. The left-hand side, I have an n by n matrix times an n by 1 vector. On the right, we have lambda times u. Lambda is a scalar. U, again, is an n by 1 vector. So to make them the same shape, I'm going to multiply by an identity matrix I. This is an n by n identity matrix. 1's down the main diagonal, 0's everywhere else. It's like multiplying by 1. It doesn't change anything. It's just making the right-hand side the same shape as the left-hand side. Having done that, I can now bring the right-hand side over, and I have A minus lambda I all times u, factor out the u, and that now has to be equal to 0. Now this is a bold 0, so it's a 0 vector. It's an n-dimensional 0 vector. So this now is a system of linear algebraic equations that happens to be homogeneous. And it has to be in the case of the eigenproblem. So we want to be able to solve this system of equations for the u, that's the solution that we're looking for, given this coefficient matrix A minus lambda I, and remembering the fact that we have a homogeneous system, the B, in a sense, is equal to 0. All right, so let's walk through the logic of this. If the determinant of A minus lambda I, the coefficient matrix in the eigenproblem, if that determinant was non-zero, then the matrix would be invertible, in which case we could write the solution, u is the inverse of A minus lambda I times 0. But that, of course, would just simply be 0. So that's the trivial solution. We do not want that. So instead of the determinant being non-zero, we actually want the determinant to be 0. If the determinant is 0, that means the system is singular. That means in this case, it'll have an infinity of solutions, but they will be non-trivial. And that's the only way to get a non-trivial solution for a homogeneous system of this type. So you have to think through that logic to convince yourself that the only way to get a non-trivial solution is if the determinant of A minus lambda I is indeed equal to 0. So here we have it written out. And it's the same as the original matrix A, but all we've done is subtract lambdas off the main diagonal. And now we're taking the determinant and setting equal to 0. Now, determinants are scalars, so this 0 is a scalar 0. It's not bold, so it's a scalar 0. When you take the determinant of a matrix like this with this variable lambda in it, you're going to get a polynomial. It'll be a polynomial equation of degree capital N. And that is called the characteristic equation. The characteristic equation, we then solve for the lambdas. So those give us the eigenvalues that are the stretch factors in our geometric interpretation of the eigenproblem. So then once we have the lambdas, of which there will be capital N of them, because that's the order of the polynomial, the characteristic polynomial, so we'll have capital N values of lambda that satisfy this requirement that the determinant be equal to 0, satisfy the characteristic equation. The corresponding non-trivial solutions, so those are the u's, those are the eigenvectors. So each eigenvalue and eigenvector come in pairs. So eigenvalue lambda 1 has an eigenvector u1. If, for example, n was equal to 3, so A was a 3 by 3 matrix, our characteristic equation would be a cubic polynomial that looks something like this. We would get the 3 roots or solutions of that polynomial, and those would be the lambda 1, lambda 2, and lambda 3 are 3 eigenvalues for the 3 by 3 matrix A. Then, and we'll walk through this through some examples, then the process of getting the eigenvectors u1, u2, and u3 that correspond to those lambdas, the eigenvalues, that will be addressed in some examples. Okay, so let's start with an example that we referenced last time, a physical example of finding the principal stresses and principal axes of a stress tensor. So remember, any continuous substance, solid or fluid, has a stress state. At every point in that medium, there are shear stresses and normal stresses, and that is given by, represented by, the stress tensor, which is just a 3 by 3, or if it's two-dimensional, 2 by 2 matrix of normal and shear stresses. We're going to look at the 2 by 2 case, the two-dimensional case, just to keep things somewhat simple. And so we're looking for those principal axes. Remember, that's the vantage point with respect to which, if I look at my stress state, at that point, I only have normal stresses, no shear stresses. That's what we're looking for. And then the principal axes are those directions. So it's the directions of the new coordinate system with respect to which we only have normal stresses and no shear stresses. All right, so we're given a stress tensor, 2 by 2, and they are such that tau xx is 3, tau yy is 3, tau xy is -1, and tau yx is -1. Now the first thing you'll notice about this is that our stress tensor is symmetric. And it turns out that that is always true because of certain physical requirements. So we won't get into that right now because that's kind of beyond the scope of what we're interested in now. But it is symmetric, and it's symmetric for physical reasons. Now let's discuss this notation just a little bit. So we have our xy coordinate system. We have a little differential element, and the faces are defined by their outward facing normals. So a vertical face is an x face. So the first subscript on the stress, tau, gives the face defined by the outward facing normal. So that would be tau x to the right, and the horizontal surface would be a tau y. Outward facing normal is in the y direction. The second subscript gives us the direction of the stress. So this would be tau xx, and this would be tau y. So it's on the x face, pointing in the x direction. It's on the y face, pointing in the y direction. So those are normal stresses. Then we have the tangential shear stresses. This one on the right face, that's tau sub x, because it's still on the x face, but it's pointing in the y direction, so it's tau xy, shear stress. Then this one, tangential to the horizontal face, is a tau y, because it's on the y face, but it's in the x direction. All right, so that gives us the tau xx, tau yy, the normal stresses, the tau xy, and the tau yx, the shear stresses. Normal, normal, shear, shear. All right. Okay, so we know, again, normal stresses are 3 and 3. shear stresses are -1 and -1. All right, so we discussed this briefly in the last video, but let's just remind ourselves what we're looking for. So the principal axes, those are the directions that we get from the stress tensor by finding the eigenvectors, and gives us the orientation with respect to which we only have these normal stresses, no shear stresses. And again, those are the eigenvectors of the stress tensor, as we proved last time. I didn't go over the proof, but it's in the book. So then the eigenvalues of our stress tensor, those give us the magnitudes of those normal stresses. So with respect to which the new orientation, the new coordinate system, those normal stresses, what are those values? Those are given by the eigenvalues. So eigenvalues give us the magnitude, eigenvectors give us the directions of these normal stresses. Now, if you're not into mechanics of solids, strength of materials, then you can ignore all these references to stresses and stress tensors. Don't worry about it. At its core, it's just an eigenproblem. All right, so ignore the terminology and some of the notation here and just focus on now we have a 2x2 system. We have a 2x2 matrix A, 3, -1, -1, 3, and we want to find the eigenvalues and eigenvectors. They do have a physical interpretation, but mathematically we're just trying to go through the steps that we just outlined a moment ago. The objective now is to get the values of lambda, we'll call them tau because they are stresses. So the values of the eigenvalues, so tau minus tau n I, all times n sub n now will be the eigenvectors. We want to find the values of the eigenvalues for which we get non-trivial solutions for the directions n, those are the principal axes. So we have our original matrix, 3 -1, -1, 3, and then we subtract off the eigenvalues on the diagonal. We set the determinant of that 2x2 matrix equal to 0 in order to find the values of tau, the principal stresses. So this is just 2x2, so we can do cross multiplication. So we have 3 minus tau times 3 minus tau minus -1 times -1. So that's here. We simplify it down to our second order polynomial. That's the characteristic equation here. So that's the characteristic equation, which we can then factor to get the two values of tau that satisfy that characteristic equation. So 2 and 4. So if you put 2 back into here, you will find that you get a non-trivial solution for n. You put 4 back in here, you'll get a non-trivial solution for n. And that's exactly what we're looking for. So we have the eigenvalues. Now we need to get the eigenvectors. Let's look at 2 first. So for an eigenvalue of 2, let's find the corresponding eigenvector. We'll call it n1. So you take your original system, subtract off the eigenvalue, which is -2. 3 minus 2 is 1. So we have 1, -1, -1, 1. If I write out this 2 equations for 2 unknowns, it's 1 times n1 minus 1 times n2 is equal to 0. The second equation is minus n1 plus n2 is equal to 0. Okay, now this is where we need to think back to chapter 1, and there's so many important aspects to solving a system of linear algebraic equations that we looked at and we emphasized in chapter 1. So remember, the determinant by definition is 0. So this is a singular system of equations. So what are the implications of that? Well, first of all, the determinant of the coefficient matrix is equal to 0. It's not invertible. Also, the rank has to be less than n. So that means we have to lose at least one equation. In this case, we can clearly see that these 2 equations are the same. One's just the negative of the other. So the second equation doesn't give us any new information. So we just have one equation for 2 variables. That's always true. We will always lose at least one equation. Again, because this is a homogeneous system, for it to have a non-trivial solution, the determinant has to be equal to 0 such that the coefficient matrix is singular. And that's the only way we can get a non-trivial solution. So we will, therefore, have to lose at least one equation. So you're always looking for those equations that are being lost. So again, one equation now for two unknowns. That means that one of our variables is completely arbitrary. So let's just pick, and I can arbitrarily pick which one. So I'm going to pick n1, and I'm just going to say it's equal to c1. I can make it whatever I want. If n1 is c1 from our equation, then n2 also has to be c1. They have to be the same so that when you subtract them, you get 0. So I can write that as my first eigenvector n1 corresponding to the eigenvalue 2 as a constant c1 times the vector 1, 1. Now this is really important. So eigenvectors are not unique. Okay? They're special. They are not arbitrary, but they are also not unique in the following sense. This constant c1 can be anything. So I could multiply this vector 1, 1 by minus 1, and I could say, okay, let me call the eigenvector minus 1, minus 1. I could multiply it by 2 and make it 2, 2, or minus 2, 2. Minus 2, minus 2. Or I could make it pi. So pi, pi. The key is all of those are valid eigenvectors because the original eigenproblem a u n equals lambda n u n, I can multiply that equation, both sides, by any constant c1, and it still satisfies the equation. So what will happen is normally we won't even write down the c1. It's implied. We know that when I write the eigenvectors 1, 1, what we really mean is any constant times that vector. And all of these other choices are equally valid. They might be less convenient, but they're equally valid. We generally like to choose numbers like 0s and 1s and 2s, keep things simple. All right, so what that means in practical terms is when you get your eigenvectors and you look at mine and compare them to mine, they might look a little bit different. And you just need to understand why and how they can be different, how they can't be different. All right, so again, not unique, but also not completely arbitrary. All right, so let's look at the second eigenvalue, 4. So now we subtract off 4. We'll go through the same exact process. We subtract off 4 off the main diagonal. So now 3 minus 4 is minus 1. So we have minus 1 times n1 plus minus 1 times n2. So we have minus n1 minus n2 is equal to 0. For the second equation, minus 1 times n1 minus 1 times n2 is equal to 0. So once again, now it's even more clear. We can see that we only have really one equation for two unknowns. Both equations are precisely the same, so I only have one equation for my two unknowns. So once again, I can pick n1 or n2 to be some constant. I'll call n2 c2. And if n2 is c2, to satisfy this equation, n1 has to be minus c2. So therefore, our second eigenvector corresponding to tau 2 is equal to 4 is c2 times the vector minus 1, 1. Once again, I could write it as 1 minus 1, or 2 minus 2. Or I could write it as minus pi, pi. All right, so those are all equally valid eigenvectors corresponding to 4. Once again, we usually pick one of the easier choices. We like 1, so minus 1, 1, or 1, minus 1. Okay, so now we've completed the math portion. So again, the physical question is what are the principal stresses and principal axes of our stress tensor? The mathematical answer is, well, we need to find the eigenvalues, eigenvectors. So we've just done that. The eigenvectors are the principal axes. The eigenvalues are the principal stresses, the values of those normal or principal stresses. So let's draw this. So in our original variables, original coordinate system, x, y, we had a particular stress state, normal stresses and shear stresses. I won't draw it again because I just drew it a moment ago. Now what we're saying is if I define a new coordinate system, x hat, y hat, with respect to which we only have normal stresses and no shear stresses. So this one I'll draw. So before, we had this orientation for our little differential element. X face vertical, Y face horizontal. Tau xx, tau yy, tau xy, tau yx. But now our orientation is as follows. We've rotated this by 45 degrees, and this vector is n1, which remember was 1, 1. So it goes off 45-degree angle in the first quadrant. And then the second vector is n2, and that is minus 1, 1. So that goes off in the second quadrant. Again, according to the signs, I could have called n1, 1. I could have said, well, that's minus 1, minus 1. Okay, well, that's in this direction. That's the same face. It's this face. Same thing here. So this face defined by minus 1, 1. This face is 1, minus 1. So everything holds. So these are the principal axes. They give us the directions of the orientation for which we only have normal stresses, and then the normal stresses themselves are perpendicular to these faces. So tau x hat was equal to 2, and tau y hat was equal to 4. And once again, those apply here and here as well. Tau x hat, tau y hat. All right, so everything is consistent. Now, one thing you'll notice here is that these two directions, the principal axes, are 90 degrees. They're orthogonal to one another. If I take the inner product of n1 with n2, I get 0. They're orthogonal. Now, of course, the question is, was that just by accident? Was that in some way we could have known that ahead of time? So we'll talk about that as well. All right, so let's just kind of wrap this up with a couple things to recognize. So again, the physical question is, what are the principal stresses and principal axes of our stress tensor? The mathematical answer is, what are the eigenvalues and eigenvectors? The process that we've just done, although we didn't describe it in this way, was in a sense a form of diagonalization. If I write the new stress tensor with respect to x hat and y hat, it's now a diagonal matrix. I only have non-zero elements on the main diagonal, 0 elements on the off diagonals. These are the normal stresses. These are the shear stresses. And so you can see that it has been diagonalized. Our 2 by 2 matrix has been diagonalized. So again, that's terminology that we'll be using later in chapter 2 that will be helpful for us. The point that I just made as well is that these eigenvectors are mutually orthogonal. It turns out that has to be true, and we'll prove that that's true for real symmetric matrices, which is the case for the stress tensor that we just looked at. Okay, now a couple of general remarks about these eigenproblems before we do another example in the next video. So mathematically, there's no reason why these eigenvalues and eigenvectors couldn't be real or complex. They happen to be real in this example. Maybe I just picked nice numbers. Maybe it's inherent to the problem. We'll see. We'll talk about that more at a later time. But in general, just mathematically, there's no reason why the eigenvalues and eigenvectors can't be real or complex. In certain applications, one or the other may be necessary. So if I'm counting sheep, there are no imaginary sheep. There's no complex sheep. They're very simple creatures. So I would require, in fact, real numbers. Not only that, whole numbers. I don't want fractional sheep. So there might be applications such as stress tensors where one or the other makes more sense from a physical point of view. And we'll see how the math follows along with that. Once again, I just want to emphasize this point that we will always lose at least one equation. So we start off with an n by n matrix A, and what we're saying is the rank of A minus lambda I, not the rank of A, but the rank of A minus lambda I is always less than capital N. It's a singular matrix, so the rank has to be less than capital N. And that's the only way that we can get a non-trivial solution due to the fact that our eigenproblem gives us a homogeneous system of algebraic equations. So we're always going to have at least one arbitrary constant. And as I said, for now, I'm actually writing them explicitly, but in the future, I'll follow the normal convention. We'll just write down the eigenvector, like in our previous example, would be 1, 1, and minus 1, 1, and the arbitrary constant is implied. We won't even bother writing it down. In this case, you will also notice that the eigenvalues were distinct. They were different. So lambda 1 and lambda 2, tau 1, tau 2 were different. They were not the same. And that also has implications, as we'll see in subsequent sections, for the behavior of the eigenvalues and eigenvectors. So I like to think in terms of road signs. So as we approach a problem, the first road sign is you look at your matrix and you ask the simple question. You can just look at it and see, is it symmetric or is it not? That's the first road sign. The next road sign will be, once you get the eigenvalues, are they distinct or not? And we'll talk about the implications of that in a later video, but that will be an important distinction as well.